Hello, I am Joseph Parsons, and I am doing a presentation on asymmetric cryptography for ICS 382, computer security. This is a primer and demo on how asymmetric cryptography works and how you can implement it in your own software. As always, this video is solely for educational purposes. The author, me, is not liable for any damages that may be incurred as a result of it. This is a good example of how you can get a start with asymmetric cryptography, but obviously, if you want to go further into it, you should make sure you are looking up additional reference material and making sure you are implementing things correctly. Peer review is always important, you know? So what is asymmetric cryptography? So in asymmetric cryptography, every member of the cryptonet holds two keys, a public key and a private key. When I want to send message to someone, I first obtain their public key, and I encrypt the message using it. That person can now decrypt the message only using their private key. As a consequence, anyone can send them an encrypted message that only they can decrypt. Relatedly, there is the concept of the cryptographically verified text. If I want to send a message that a person can be sure came from me, I can encrypt it using my private key. Now, people will only be able to decrypt it using my public key, which is really everyone. Everyone can get my public key. But because it had to have been created with my private key, the key that only I know, no one else will be able to send a message posing as me. This is why it's commonly used in emails, for instance. So let's compare asymmetric cryptography with symmetric cryptography, okay? At their core, symmetric cryptography only has one key, a shared secret that can be used for both encryption and decryption. Asymmetric, again, has the two keys, the public and private key. And communication between two parties will have two sets of two keys, 4 keys total. So it is simpler to perform key management with symmetric cryptography, but it's also less secure. If someone determines the key we're using, then they are able to decrypt it. Anyone who finds that key is able to perform decryption activities. It is much easier to manage the sharing of keys when you have a separate public and private key. Now, because of the algorithms used, symmetric encryption is considerably faster. Asymmetric relies on mathematical operations that are very hard to do in one way, but very easy to do in the other way. But as a consequence, it can be very slow, at least compared to symmetric cryptography. Asymmetric cryptography also has easier and more secure key exchange, as I kind of discussed. You can safely distribute your public key to anyone. It doesn't matter who. As long as your private key remains secure, the encryptions or the communications will still be encrypted. Asymmetric cryptography also supports much larger cryptonets as a consequence of all this. You can have thousands of users communicating, and they can all share their public keys, and anyone can decrypt messages that were encrypted with their private keys, and everything will be secure. It's very hard to manage a cryptonet of 1,000 users using symmetric key cryptography, because as soon as one user leaves, everyone has to rekey, and that's a very difficult process when you have 999 users who need to now rekey. It has to happen constantly when you have at that scale too. So for large cryptonets, asymmetric really is a must. There is also a hybrid approach that uses the concepts of both. Some people might actually consider this just pure asymmetric cryptography, but I really consider it to be more, it is both. And in this approach, what will happen is we'll have a shared symmetric encryption key, but we communicate the shared symmetric encryption key using asymmetric concepts. So for instance, let's say the secret key is I love Bob. I love Bob is now used to encrypt and decrypt messages. If I want to send this shared secret over to Bob, I will, instead of just sending it in plain text, I can encrypt it using Bob's public key so that only he can decrypt that shared secret using his private key. As a result, we have safely communicated a shared symmetric key that really is not going to be exposed to anyone because of the asymmetric concepts employed. And this is a very common way of doing things. SSH uses it for the initial connection. HTTPS and TLS use it for the initial connection, as do many others. We'll be looking at WhatsApp in just a second. So messaging apps will commonly use this as well. So yeah, let's take a look at WhatsApp. There's three concepts here, and these are all discussed in the white paper that you see below. It's the concept of how messages are exchanged on the WhatsApp platform, how attachments are transferred, and how group messages can be relayed. First, there's this concept of ratcheting. Okay, so we have previously agreed on a chain key. We'll call that CK. To generate a new message key for encrypting messages, we can perform a hash on CK. And now, in order to ensure that you can't derive the chain key from the message key, we perform a second different hash operation on the CK and set it to that value. This makes it very difficult to convert MK to CK. There's no really clear operation between MKK, hash K, and hash 2K. What you could do is unhash the unhashed 2 of CK, and you'll get MK, but this is such an incredibly complicated operation that in effect, you simply cannot derive MK knowing CK, or vice versa. So yeah, let's see how we send messages using this protocol. So A wants to send a message to B, all right? A will ask the signal server, in this case WhatsApp, for B's public key as well as a nonce public key. A will generate a shared secret using B's public keys and A's private key. It uses both for additional protection in this case. A sends a message to B with the shared secret as it's encrypted. B will receive the message as well as A's public key information from the signal server and will be able to decrypt the message using A's public key and B's private keys. Both parties will now generate chain keys from this shared information, the information that they have had together, and will be able to encrypt and decrypt each message by ratcheting the chain key. Now, this is actually really simplified. There's a fair bit of signature validation going on as well in this process as it applies in WhatsApp. There's additional tricks that, for generating the chain key. So this is very simplified to try to make it actually understandable to someone who has at least a basic understanding of encryption, but not, fluent understanding and exactly all of the concepts involved. So yeah, you can read the white paper if you want to go into the thick of it. Now, I talked about this nonce key pair, and I want to go into a bit more detail on that. So what happens here is when you get an account with WhatsApp, every user is going to generate a handful of public and private key pairs, and they will be stored, the public ones will be stored in the WhatsApp server. This will be a collection of nonces. When the server runs out of nonces, if it doesn't have any more, communication can still happen, but it won't be using the nonce anymore. As a result, if we have the nonce, then a communication between A and B is still going to be secure, even if B's permanent private key had been obtained by someone else in the intervening time. It's just a bit more secure by using the nonces. If they aren't available, then that additional security won't be available. In practice, most public key cryptography doesn't really use the nonce concept that I've seen. Enough of it does, but it often isn't used. This is more specifically an added protection available to a messaging platform, but it's not required to have most of the benefits of the asymmetric encryption. It's a good concept to be aware of, and it could be very useful if you ever want to implement something like this, to be aware of the concept of these nonce key pairs and use them. So let's take a look instead at how WhatsApp file transfers work, okay? To perform a file transfer from A to B, A will encrypt the file using a randomly generated key, we'll call that K, and will also find the hash of the file as S. A will upload the file to some server, typically the WhatsApp server, and send a message to B containing the server URL, the encryption key K, and the hash S. Because this message is being encrypted with a shared secret that no one else is going to have, we can trust that no one else is going to be able to read the message. No one else is going to be able to see what the random shared secret K is, or the hash S. So only B will be able to read this message. B can now download the file and verify that the file matches the hash in that message S, and will decrypt it with K. Because of the hashing, it ensures that it is the valid file, and because the shared secret K hasn't, it shouldn't be available to be stolen, you can be sure no one else is going to have access to this message, including the WhatsApp server that's storing it. The WhatsApp server has no idea what the shared secret is. That was only sent in a secure message to B. So next up, let's talk about the concept of group messages, where multiple users want to converse together. Okay, to do this, let's say A wants to initiate the group message, okay? A will send a message to B, C, and D. This message is going to contain a random chain key generated by A. In order to send this chain key, A establishes a secure asynchronous connection with B, C, and D, the same way A will do so if A was trying to send a message to any of those users individually, as we saw here. Okay, so these users have now received this message. No one else can see it because it was using their own private keys. It was encrypted using their public keys, and they have to decrypt it using their private keys. Now, any one of those people can send a message to the WhatsApp server that is encrypted using a message ID ratcheted from the chain key, okay? So B sends a message to the server sends the message to A, C, and D, and A, C, and D can decrypt the message by ratcheting the next item in the next message key from the chain key, okay? Now, the significance of this is that, you have to keep the messages in order. That's why we send to the server, because if a message from A arrives before a message from B for somebody, but not for somebody else, the result is that the ratchet is being applied in the wrong order. So in order to maintain order with the ratchet, the WhatsApp server has to coordinate how individuals receive group messages, okay? But otherwise, it works really well because WhatsApp is simply unable to decrypt the messages. WhatsApp was not involved in establishing the initial chain key, so WhatsApp has no idea what the initial chain key is. So in summary, the Signal protocol as a whole, and WhatsApp in particular, uses secure asymmetric cryptography to establish shared secrets between multiple users. It may use an additional nonce pairs for additional security. Individuals can then use the shared key to ratchet a message encryption key for every message, or a very similar approach for files. They can even send encrypted messages to a server for relay, as with group messages, and if one of the users is offline, trusting that the server simply can't derive that message key because it has no idea what the chain key is, and it can't figure it out. WhatsApp does also perform signing to verify the identity of users. B can't pose as A and send a message to C because of the signing, but I want to get too advanced in that, so I'm going to skip talking about that. Next, I want to look at implementing simple cryptography in a number of languages, okay? So I'm going to look at PHP, Java, and C# and just see what libraries are available in those. I will also have a demo, a very basic demo using PHP, okay? So in PHP is a really interesting one. PHP standard library has always been a little bit weird at times. Things being added and deprecated constantly. The current best option in PHP is OpenSSL. OpenSSL has been available in PHP since PHP 4, but until recently, mcrypt was the default choice. I can't say why mcrypt was used over OpenSSL, but in my experience, if you're performing symmetric encryption, you'd usually use mcrypt. OpenSSL was only ever used for asymmetric encryption because mcrypt didn't have any comparable support, okay? And in fact, the big change now is that beginning in PHP 7.1, mcrypt has been deprecated. It's now no longer maintained, and the PHP developers don't want to have to maintain it themselves. So they are going to remove it in 7.2 and just encourage everyone to use OpenSSL for most things that mcrypt could have been used with. It's actually pretty easy to port. I did it myself with a small application using symmetric cryptography. So a port from mcrypt to OpenSSL isn't too difficult. However, PHP 7.2, which is yet to be released, will also add libsodium. Now, libsodium is a much newer encryption library. It's more full-featured. It uses better Saner defaults. And it's a lot easier to screw up. It is not currently in PHP. Like I said, it won't be out there until 7.2. But when it's available, I personally would recommend using it as much as possible. You're less likely to screw up with it, and you're going to be using stronger encryption as a result. Okay. Now, Java, there are two modules that are used in Java for most cryptography. There's JavaX Crypto, which is used for standard, encryption and decryption. There is also Java Security, which is used for key management. So if you wanted to obtain a private and public key, you'd be using Java Security for that. If you wanted to encrypt using those, you'd be using JavaX Crypto. Now, at the bottom there's a really good example I found. I tested it out. I think it's a really, if you know Java and you want to play with asymmetric cryptography, a really good example is available right there. Okay. C#, that's all in system security cryptography. It's all right there, easy to use. RSA crypto service provider is available for asymmetric operations, while AES crypto provider is available for symmetric ones. You can look at the MSDN link there for documentation on those two libraries. So now I'm going to go and show a very basic demo of PHP's OpenSSL functionality, okay? And I'm going to show both synchronous and asynchronous functionality using this, and also why you kind of have to use the hybrid approach I talked about at the beginning if you want to encrypt a lot of information asynchronously using PHP, okay? All right, so to start here, we have a very basic demo of generating a key pair using the OpenSSL functionality. It's kind of weird. It doesn't make a lot of sense. This functionality is specifically designed for certificate signing. So it wasn't intended to be used for this, but it can be. So let's use it for this. It is the only functionality available in PHP 7.1 and lower that is available for asynchronous crypto. So it's the only choice we got, and it works. It works just fine, as I'll show you. So we get a key pair using OpenSSL pkey new. We can specify the key bits if we want to. If we want to encrypt a large message, and I'll explain this in more detail in a moment, but if we want to encrypt a large message, this number should be bigger. We then export the private key from our resource. We use OpenSSL pkey export that, and that'll save it in the private key variable here. We can use OpenSSL pkey get details, which will return an array of public key information, and the key index is used to store the public key. So we simply read the key index into the public key variable there. And then we just show it out here for us. So here we see the keys that have been generated by that. It has a fairly short public key, a fairly long private key, as well as a random key that we might be able to use later. Okay. Using this, we can now go into our demo synchronous cryptography function, and we can use a public key to send a message to our friend. We'll assume we know our friend's public key. We know this information. Our friend only knows this information. We don't know it, okay? And we can encrypt any text. Let's say hello. We have encrypted text. I'll show you how that works in the source code, okay? So to do this, we send the text into OpenSSL public encrypt. That's right here. OpenSSL public encrypt will store the information in the second variable encrypted right here. And it will use our key listed here to perform the encryption. We're also using OpenSSL, a certain padding variable here, a certain padding constant, I should say. The default is not secure. It is vulnerable to a chosen cipher text attack, as you can see here. The Zend framework, which is also developed by the same PHP developers and is available for PHP, it has its own RSA library, which will use this specific one to be the most secure. You don't have to use the Zend library. Just make sure you are using the more secure padding function shown here to perform the public encryption. Okay, that runs, and we get our encrypted text. For ease of use, this is currently encoded in base 64 instead of just binary. Now, let's say we want to decrypt that. We are the friend now, and we receive this text from our other friend. And we know our private key. Our friend doesn't. So we can insert our private key. We can use our private key to perform the decryption. And only we can do this because only we know the private key. And it'll then show the decrypted text. Nice and easy, right? It's really neat. And I'll show you the function on that one as well. It's basically the reverse OpenSSL private decrypt. And you pass in the ciphertext, or the decryption text, and that'll store it in the decrypted variable. We pass in our private key, and again, we use the correct padding constant. All right, nice and simple. However, there's limitations here. We can't encode a very large string here. So right here, for instance, is 100 digits of pi. Doesn't work. It's too long a text for our public key. It is simply too long. Now, in that specific example, I believe if we generate a longer key, we can encrypt it. So the length of the public and private key pair does affect how much text we can encrypt. You can see right there we do have valid encrypted text with the 4096-bit key pair, okay? But we can't do it. Well, there's a limit here. We can only go so far. For one thing, if you try generating something much longer, like say 386, that'll take a very long time. It is doable, but it'll take a very long time. And it also won't even work. I don't know the exact reasoning behind it, but the OpenSSL, the way it's designed, I assume because of the certificate usage, there is a hard limit on how many bytes you can encode. So instead, we have to go the hybrid approach, which means instead of encrypting our text using the asynchronous approach, we can encrypt a shared key using the asynchronous approach. And then we get our encrypted shared key, and we can send that to our friend instead. And we can also separately, and using our original shared secret, this one right here, we can encrypt a much longer message. Here, for instance, is 1,000 digits of pi. We can successfully and easily encrypt this using symmetric encryption, okay? We now send this text to our friend, okay? And so our friend, who has received the asynchronously encrypted shared secret, now performs the decryption using his private key and the message, the encrypted text he received. He now has the key. And this was transferred asynchronously. No one can figure it out without having the private key. But you can see it is the correct same key. And he can then perform the decryption symmetrically. Oh boy. I'm sure I've said synchronously instead of symmetrically. Just pretend I didn't do that. I'm not going to reshoot. He can now use the key he has obtained using the asymmetric process to decrypt the symmetrically encrypted data. And there we have the 1,000 digits of pi. This works really well, everything else considered. And it can be used for basically any number of text. We can go for a much longer one if we wanted to. So assuming this is the same code and we've already transferred that, we can encrypt a much larger bit of text synchronously. You can see that is quite large, right? Oops. But because we transferred a very short shared secret, which has been securely transferred, it works without flaw. Okay, so this is a very simple demo of how this works. I will be posting a link in the video description to the source code for these 5 files. Now, as for how we perform the symmetric encryption, we still use OpenSSL, though instead of public encrypt and private decrypt, it's just OpenSSL encrypt. The exact way this works, I don't want to focus too heavily on how synchronous cryptography works. There are plenty of guides for it online. But you can see the source code here. We're using AES 256 and the CTR. There's plenty of other options available for that. I think CTR is probably the most secure available in 7.0 anyway. I think 7.1 introduced a more secure cipher suite there. But yeah, and then we can decrypt it in just the same way. So to recap, asymmetric cryptography is powerful, but it can be very limited. You can only efficiently transfer so much information using it. So instead, we use asymmetric cryptography to exchange symmetric keys, and doing so combines both the speed of the symmetric approach and the security of the asymmetric approach. Asymmetric cryptography is used in a number of noteworthy applications, such as WhatsApp, HTTPS, TLS, and SSH. They'll all do it in the hybrid approach. Thank you. Again, I am Joseph Parsons, and I hope this has helped you understand the ideas behind asymmetric cryptography at least a bit. Again, the source code used for the demo should be available in a link in the video description, all right?